Welcome to the second week of winter school. We're very glad to have been joined by the speakers for the second week. So our first speaker is Geordie Williamson, and he's going to tell us about Kazhdan-Lusztig polynomials, representation theory, geometry, and combinatorics. So a word for each of the 5 days. Please welcome Geordie, and we look forward to his lectures.
So thank you very much, Masood. So this course is about Kazhdan-Lusztig polynomials, and I want to look at them through various different lenses. So we're going to look at them mostly through the lens of combinatorics, but also through the lens of algebraic geometry, and also through the lens of representation theory. I just want to start talking about what these summer schools or winter schools are and what you can expect to get out of them. Okay? Because I think there's definitely a change that happens when you start to go to these kind of events. So here is a quote which I think is very beautiful. It's from William Thurston, who was one of the giants of 20th century mathematics, who passed away a couple of years ago. So it's from this article called On Proof and Progress in Mathematics. So it was a response to an article by Jaffer and Quinn, which is quite a famous article. And Jaffer and Quinn were saying that the influence that physics is having on mathematics is very bad. And suddenly we're moving away from proof. And this is a big problem, and we all need to be very careful. Okay? And Thurston is talking about what mathematicians do and what we value. And it's an incredibly inspiring article. Okay? So I just want to quote from it. So this is from what I think it's around about the 4th page. So he says, this brings to the fore something that is fundamental and pervasive, that what we are doing is finding ways for people to understand and think about mathematics. So the context of this is, what are we doing as mathematicians? So Jaffer and Quinn says, our job as mathematicians is to prove theorems and decide what is true and false. And Thurston is saying, no, there's something more subtle going on. Our job as mathematicians is to find ways for people to understand and think about mathematics. And then he discusses this really famous episode, which is the 4-color theorem. So the rapid advance of computers has helped dramatize this point, because computers and people are very different. For instance, when Apple and Harkin completed a proof of the 4-color theorem using a massive automatic computation, it evoked much controversy. I interpret the controversy as having little to do with doubt people had as to the veracity of the theorem or the correctness of the proof. Rather, it reflected a continuing desire for human understanding of a proof, in addition to knowledge that the theorem is true. So, you're probably familiar with the 4-color theorem, and you're probably familiar with the fact that you can ask a computer, can you analyze the following 4,000 cases and tell me whether it's true or not? And the computer says yes. But this is an interesting example of mathematical proof, yeah? Because we could write a program that prints this out and says case 1, case 2, case 3, case 4, case 5, case 6, case 7. But no human could ever read this proof. And I think that, you know, there's some possibility in the future that some computer proves the Riemann hypothesis, and it happens to be 10 billion lines long. Okay? And no human can ever read it. And would we be happy with that situation? Okay? So the reason that I'm talking about this is because it ties into what you can expect to get out of a summer school. So I cannot do theorem proof. I cannot justify every step that I'm taking. What I'm trying to give you is understanding. Okay, that's very important. Okay? And understanding can take many different forms. It might be an analogy, it might be a picture, it might be a proof. Okay? So it's very different to a course where we see theorem proof. Yeah? And it's very important as you develop mathematically to start getting used to different forms of understanding. Okay, so, and also I set myself a little task for this lecture series, which is to start every day with a quote. And so I've had lots of fun finding nice quotes for you. Okay, so now we go to maths. So one more point. This is something that I believe very strongly, is that software is very powerful for visualizing exploration play. Okay, I was just watching this incredibly inspiring interview with Gromov on the Simons Foundation website. And he says, what makes us human, what fundamentally makes us human, is our ability to play. It's not the ability to feed ourselves extremely efficiently. It's our ability to play. And playfulness coming through software is very powerful. Okay. So we'll try to, so Joel has written some amazing software for visualizing some of the things we'll be discussing called levers. And we'll have some exercises to do with playing with that software. Okay, so this course is essentially about the symmetric group. Okay, so the symmetric group is the set of permutations of 1 up to n, and it is a group under composition. Okay? So you might think that a group is some kind of symmetry. So it's a bit funny to call a group a symmetric group, okay? But is the most, probably the most fundamental group out there, or one of the most fundamental groups out there. So here's a permutation. So this is a permutation that says 1 to 3, 2 to 2, 3 to 5, 4 to 1, 5 to 4. And the traditional ways of thinking about what a permutation is, that you saw perhaps in linear algebra, is you can see it as this kind of array notation, where you list 1, 2, 3, 4, 5, and you say what it does to 1, 2, 3, 4, 5. That's the, or cycle notation. So I hope that you're familiar with this stuff. If not, just ask me, or ask Joel, or ask someone else. But these will not be so useful for us. The most useful 2 notations for us will be the string notation. So here we just take the array, but we take as read like what happens at the top. So this is saying 1 goes to 3, 2 goes to 2, 3 goes to 5, etc. Or this diagram. This is actually the most useful way for me. This is actually really, when I think about a permutation, this is what I think of. So, you know, this is indicating that 1 goes to 3, 2 goes to 2, 3 goes to 5, etc. Okay. So you can visually see the permutation. And in string notation, composition is stacking of diagrams. So if we were to compose this with this permutation, we'd stack these on top of each other, and then we would have kind of double crossing here, which we could then undo. So this is, if there's one fundamental kind of object in this course, it's the symmetric group. So we're representation theorists, and so we should get used to the instinct that if you have a group and there's a natural representation around, look at the representation too. And this is a non-trivial thing. It was not my instinct when I was a student. When I saw a group, I thought, I want to understand it as a kind of combinatorial object. I didn't want to understand it as a linear algebra object. Okay. But the more that you understand things as linear algebraic objects, the more that you realize that it's powerful in the long run. So Sn acts on Rn by a permutation of coordinates. So this is just saying that Sn can also be realized as permutation matrices. And it's faithful. Yep, if I know, I can just read off my permutation from what it does on the basis. And as representations, this splits up into 2 pieces. I have the trivial representation. So if I look at the line consisting of all coordinates equal, 1, 1, 1, 1, 1, 1, 1, then, and I act by a permutation, this is fixed. Yeah. And so it splits into trivial plus natural. And the natural representation is the one that we're going to care about. And you can ask, how do you like actually work with this representation? And the way that I like to think about it is that, so this here I've drawn the picture for n equals 3. So what you imagine is that so imagine here's my E1, E2, and E3. let me know, Hawaii, if this is annoying me kind of gesticulating with my hands. And I have this vector 1, 1, 1, 1, 1 that sticks out of the positive orthant. Now, I imagine that I'm out at that vector and I'm looking back at the origin. And I see my vectors E1, E2, E3 sticking out. And this is the picture of the natural representation. Yeah? So the permutation that, for example, takes E1 to E2 to E3 is a rotation in this plane. The permutation that swaps E1 and E2 and fixes E3 is a reflection in this plane, etc. Okay, and it's really useful to think about the natural representation in this way. And if you would like a little thought experiment, try to think to yourself, if you're not used to thinking about this representation, what can I read? What kind of linear algebra stuff corresponds to stuff in group theory? So how can I read off? So for example, you could read off the cycle type from the eigenvalues. How do you do this? Okay. Again, like there's many different levels in the audience here. So if something sounds too complicated, ignore it. If it sounds too easy, ignore it. If it sounds like it's the right level for you, have fun. Yeah. That's the natural representation. We'll come back to this several times in this course. So now we're going to study the Coxeter presentation of the symmetric group. So we have these simple transpositions. So this is the permutation that swaps I and I plus 1. And I'm calling this TI throughout the course. So TI is the transposition that swaps I and I plus 1. And it's simple because it swaps two adjacent numbers. It squares to be the identity. If I swap 1 and 2 and then I swap them back again, I get the identity. So that's this relation here. Okay, and now I can see this in my diagram language. If I stack this diagram on top of each other and then stack it again, these just undo and I get the identity. And then we have two other relations that are enormously important. The so-called braid relation. So TI plus 1 TI is the same thing. So this results in the permutation that swaps I and I plus 2. And I can write that permutation in two different ways. And if Ti and Tj are distant, so in other words, if I minus j is bigger than 1, then they commute past each other. And we have the following beautiful, so this is the first theorem, that this is a presentation for the symmetric group. So we have generators, the simple transpositions, and relations. So I'll write these relations in several different ways. So this is the first way I want to write it. So Ti squares to be the identity. Ti and Tj commute when they're distant. And we have this braid relation when they're next to each other. But you can repackage these two efficiently in this way. So Ti Tj to the order of Ti Tj. So if you, so Ti T plus 1 has order 3. Ti Tj has order 2. So, you know, this way, this relation here repackages these two. Okay. And proving that this is a presentation is not difficult. So you just need to show that. So we've seen that these relations hold. You just need to see that there's enough of them. You've got enough relations. And that is the first exercise on the exercise sheet today. Okay, a very fun exercise. And also, it goes without saying, but please do not hesitate to ask a question. Please do not hesitate to hit the brakes if I'm going a bit too fast. So now I just want to briefly discuss the length function and reduced expressions. So this is the length of a permutation. So the number of inversions. Okay, so this is the number of pairs I and j, so I less than j, such that the permutation swaps them. And in a diagram, this is the number of crossings in a diagram without double crossings. Okay, so here's my length, here's my element from before. I could either look, you know, what are the elements I and j such that, for example, here I have 1, this is like 1 and 2, and 3 is bigger than 2. So 1 and 2 is part of one of my inversions, etc. And I can look through my word and count all the inversions, or I can do what I usually do, which is just draw a diagram and count the crossings. The length of x is the minimal length of an expression for x in the generators S. So that's a beautiful basic fact. So the statement here is that I can find a reduced expression for this. So I can find an expression for this element in my generators S, which involves exactly 5 such generators. Okay. So an expression of minimal length is called a reduced expression or a rex. Okay. At some point in my life, I started saying reduced expression so often that I thought it would save me enormous time by like saving a second every few minutes by saying rex instead. Okay, so this is an example of a rex, whereas this one is not. Maybe, can someone tell me why it's not? And maybe the following rule is good. If I ask a question and you feel it's super easy, don't answer it. Yeah? If you feel it's like Goldilocks, answer it. Yeah? If you feel it's too hard, have a go at answering it anyway. So, yep. Exactly. Yep, so I can cross out this one, and then I get my expression from the left. Yep. So basically, it's a little bit tricky, yeah, because, for example, this guy, if I did S1, whoops, S1, S2, S1, S2, is that reduced? Or, sorry, so one of the things that I meant to say is that I reserve the notation TI for a simple transposition in the symmetric group, and then SI just denotes any simple transposition. T1, T2, T1, T2. Okay, this is not reduced either because this is the same thing by the rate relation as T1, T2, T2. Okay, so this is also not reduced. Okay. So reduced expressions play an enormously important role in this subject. And so getting used to reduced expressions is very valuable. Okay. And you can have an enormous amount of combinatorial fun with reduced expressions. So an expression is any word in the generators. And its endpoint is what I get by just multiplying out these generators. Okay. Where does the notation come from? So I won't, yeah, so a sub-expression, there's various ways of phrasing what a sub-expression is, but in this course, we remember that we fixed an expression, and a sub-expression is simply a 0-1 sequence indicating which simple reflections we take and which ones we don't take. So for example, I'm thinking about, so here I have my 0-1 sequence, which is giving me a sub-expression, and this is telling me kind of, I take, if it's a 1, I take S1. If it's a 0, I don't take S1. Okay. So, and this is very important, the Brouillard-Stroll. So where does this terminology endpoint come from? You can think about an expression as a journey through the group. You start off at the identity, and then you multiply with S1, and then S2, and then S3, and then S4, and you keep moving around the group. Yeah? So a sub-expression is a recipe to modify that journey. So you're journeying, and then 1 says you should do what your expression tells you to do. 0 says don't do it, stay where you are. And that's encapsulated by this Brouillard-Stroll. So I start at the identity, and then I move if E1 is 1. If it's not 1, I stay where I am. Okay. So for every expression, I have sub-expressions and I have a corresponding Brouwer stroll. And you can think about, a stroll is leisurely, yeah? So, you might go over here and then you might, no, go back here. Yeah, that's what a Brouwer stroll encapsulates. That's what a sub-expression encapsulates. A reduced expression is like, I want to get over there. That's a walk. Yeah. Whereas a stroll is. So here's some examples. So here are my elements of S3. So I'll very often in S3, I'll just say that S is S1 and S is T1. That statement here. This is very, very common, often my conventions. So here are my 6 elements inside S3, the 6 permutations of a 3-element set. And here's my walk. Okay, here's my expression. So what this guy does is I go S, T, S, T, S, T. Okay, so this expression here is a lap through the elements returning to the identity. Okay, so if I take as my sub-expression 1, 1, 1, 1, 1, 1, 1, my stroll just does a loop. But if I did 1, 1, 0, 1, 1, 1, I would go 1, 1, 0, 1, 1, 1. Okay. And you have to get used to multiplying in the symmetric group to make sense of these. Okay, so that's what this mysterious picture looks like, is indicating down here. Okay. So now we get to, so everything up to now is basically kind of combinatorial and not so difficult. And now we get to something that looks of exactly equivalent difficulty, but is actually very, very subtle. And that's Brouwer order. So throughout, we have, so remember that we have W is Sn, and this contains S, the simple transpositions. And now we have T, the transpositions. And these are exactly the conjugates of the simple reflections, if you know your conjugacy classes in Sn. And these are also, this is a nice little thought exercise, or you should do it if it's the Goldilocks level of difficulty, is that these are exactly the reflections in the natural representation. These are exactly those elements of Sn that act as reflections in this representation I discussed before, i.e. that they fix the hyperplane and send a vector to its negative. So now we have this definition. So this is the thing that's actually very subtle, but kind of, one can underestimate at first glance, is this statement, X is less or equal to Y if X may be obtained as a sub-expression of a reduced expression of Y. So this gives rise to a partial order. So it's not obvious that this gives rise to a partial order. So this will be seen in the exercises. And here we have the Brouwer order on S3. So we have STS. We can find everything as a sub-expression of STS. So everything is less than STS. ST, we can find S and T as sub-expressions. TS, we can find S and T. But for example, we can't find TS as a sub-expression of ST. Okay. And you can see this, one of the statements that we will use later on is that you can get all reduced expressions for a single element by applying grade relations to a fixed reduced expression. So that tells us that this is in fact the only reduced expression of this element. Okay. So, question for you. Why is it not obvious that this is a partial order? What would I need to check here? Yep. Exactly, yeah. No, that's perfect. So when I said x may be obtained as a sub-expression of y, I didn't say that that sub-expression has to be reduced. And so transitivity is not obvious. Yeah. But yes, Masood?
So if we remove the word reduce in that definition, then it becomes from.
Yeah. So can someone just before so there's two hands went up. Hang on a second. Can someone explain to me why Masood, why what Masood said is correct?
For the Hawaii people.
Apologies, Hawaii people. So Hawaii people, Masood asked if I replace, if I remove reduced. So is it wrong that x is less than or equal to y if x may be obtained as any expression of y? So this is indeed incorrect. And now I'm asking why this is incorrect. I don't think I understood that.
So you take any expression y,
Yeah,
you add expression of x at the end of that expression.
but that would no longer be an expression for y. Oh, perfect. Yeah. So take y, take a reduced expression for x, add its inverse. You have some enormous expression. Yeah. So that shows that if in the non-reduced version, everything is less than or equal to everything else, that's not a very interesting partial order. In fact, it's not partial order at all.
Okay, let's just work out this.
Rumblings will be over soon. So Chris had a question.
Yeah, so what if we had the word reduce for x?
So this would be the same thing. What was the question? The question was, what if we add the adjective, a reduced expression of x may be obtained as a sub-expression of a reduced expression for y. So this would indeed give an equivalent definition. Yeah. And Madeline, I think, had a question. Oh, okay. Madeline had exactly the same question as Chris. Excellent. That's Brouhaha order. Here's Brouhaha order on S4. So we saw S3. Just so that you have some kind of idea of this subject, you know, n factorial grows very fast, yeah? So like you might understand everything for S3, you get to S4, it's complicated, you get to S5 and it's already like out of the, beyond the realms of any kind of hand computation, yeah? It's a, you know, mucking around with symmetric groups really teaches you about that n factorial grows very fast, yeah? And so this is essentially the last example that you can do reasonably by hand. This is the Brouhaha order on S4. Okay. And probably, if you're interested in this subject, you should do this at least once in your life. Yeah. And not just plug it into Python as I did here. Brouhaha order is the source of many mysteries. So I am unaware of a formula for the cardinality of the set of elements less than a general X, for example. And you can ask more subtle questions like how many elements are less than x of a given length. This is even harder. Okay, so I should get a little bit of wriggle on so that I'm finished by 20 past. So what I want to explain now are affine reflection groups. And affine reflection groups, when you start off with them, it seems more complicated. But what you get is a visual language for understanding Coxeter groups, which then actually ends up being very useful for your understanding of symmetric groups. So I find it a beautiful example of where sometimes someone comes up to you with a generalization and you're like, no, I just care about this. I hate generalization. Yeah? I don't want to listen to your generalization. And then, you know, sometimes you're right. Sometimes they're just generalizing for the hell of it and you should not listen to them.
But sometimes that generalization can give you real insight on your basic problem. Yeah? And this is what happens with affine reflection groups. I'm much better at imagining the symmetric group thanks to what I've learned from affine reflection groups. Okay? So I find that a very beautiful process. So what's a reflection? I hope we all know what a reflection is. So here's a vector space. It's a blue orb here. Here's the origin. I've taken a vector n. It's a Euclidean vector space. So this means it's a real vector space with a positive definite inner product. And I've taken a vector here of unit norm. Okay. So now the following transformation, what does it do? Like, let's stare at this formula for a second. So if I plug in n, it sends n to n minus 2 times the inner product of n with itself times n. The inner product of n with itself is 1. So this sends it to n minus 2n, i.e. it sends n to minus n. First piece of information. Second piece of information is that if something is orthogonal to n, i.e. its inner product with n is 0, it does nothing to it because this term is 0. So this means that everything in this hyperplane, this is a two-dimensional picture, but in general I'm thinking this is a hyperplane, is fixed and n is sent to its negative. So it is indeed a reflection. This is what we call a real reflection. Yeah. Here is an affine reflection. So now I'm allowing myself to reflect in a hyperplane consisting of stuff which is gamma away, stuff which has inner product with n to be gamma is the hyperplane of distance gamma away from the origin, parallel to this one. Yeah. And now, via exactly the same kind of thought, you can convince yourself that this formula defines an affine reflection. So an affine reflection group is a subgroup generated by reflections, by affine reflections. And now we have this somewhat mysterious condition that it's proper. Okay. So what this says is that if I take two compact sets, and then I look at the stuff in my group that takes this compact set and intersects with this compact set, that's a finite number of elements. Okay. So basically, I don't really want you to worry about this condition too much. It just says that in some sense, my reflection group is discrete. Okay. So for example, you might know that any orthogonal transformation is generated by reflections. So you can write any orthogonal transformation of a vector space as a composition of reflections. But an orthogonal group is a continuous group. I don't want to consider such things. I just want to consider stuff that it looks discrete in some sense. Okay. So I'll show you an example. So firstly, a very important basic example is all affine reflections in the integer points of the real line. Okay. If you've never thought about that before, that might be a kind of wacky group. Very nice group. Yeah, we'll understand it much better in one slide's time. Okay, so for example, I'm considering like stuff like I reflect about 0, so I send x to minus x, and I reflect about 1. So I send 2 to 0, 3 to minus 1, etc. Okay, so that's a nice affine reflection group. Here I consider this following very nice hyperplane arrangement. So it's like equilateral triangles paving the plane. And then I consider all reflections in all these hyperplanes. I look at the group that they generate. Okay, it might seem like this is a pretty wacky group. Yeah, if I didn't know any theory, I wouldn't really know how to think about this group. Huh? So these are two examples of affine reflection groups, and also a finite reflection group is an example of an affine reflection group. Yeah. So that's kind of important, so I'll just write that down. So finite is an example of an affine reflection group. So for example, so Sn the symmetric group, we said first it's a group, but then I gave you a beautiful representation of it. And it's generated by these simple transpositions, and these transpositions act by reflections. And therefore, this is also such a group. Okay. So how do we understand any such group? So this is kind of bonkers. So, I'll go over these slides reasonably quickly now. I mean, I have 15 minutes. But it's a kind of, I don't know, it's a magical thing what we're going to see in the next few slides. And it took me about kind of 4 years to understand properly. Okay. So, try to understand it and then try again to understand it. And then at some point, you just realize that it's the most beautiful thing in the world. So what we do is we look at, in order not to be intimidated by this, just think about the triangular case. Yeah? So what we look at is, so here we have this infinite collection of hyperplanes, and we're considering the group generated by this. And the first recipe is to consider all reflecting hyperplanes, and I'm going to call that capital Phi. Okay, so that's all these hyperplanes in this direction, all of these in this direction, and all of these in this direction. So it's infinitely many hyperplanes. And now what we consider is we take our vector space and we delete our real vector space and we delete all of these hyperplanes. And we get a whole lot of connected components. In this particular case, we get a whole lot of triangles left over. And then these we call script A. And these are the alcoves. Now we fix one such alcove and call it fundamental. Okay, that's my fixed fundamental alcove. And then we look at the reflections in the walls of that alcove. Okay, so this is saying H intersects the closure of this alcove in codimension 1. So like this would be a wall of such an, this would be a wall of this alcove, but this would not. Yeah? So this hyperplane intersects the closure in something of dimension 0. So it is not a wall. Now comes the bonkers thing. So this is the structure theorem. So firstly, our group is generated by the reflections in the walls. So this crazy infinite group is generated by these 3 affine reflections. Okay. Secondly, we have a beautiful fundamental domain for our group. The closure of this fundamental alcove is a fundamental domain. Okay. So that means that no matter where I am in my vector space, I can recover a unique point in this fundamental domain by using my group. I can come back home and identify myself with a unique point. Yeah. And this is a Coxeter group. So it has a very beautiful elementary presentation. It's generated by these reflections. And if I think about 2 of these reflections, so let's say I think about this reflection and this reflection. So their composition, nice thought exercise. If I take 2 reflections in 2 hyperplanes, their composition is a rotation through an angle twice the angle between those hyperplanes. Yeah? So now I can just look at that angle and immediately decide the order of this composition. Yeah? If this angle is like 60 degrees or something, then the composition is going to be 120, so that's going to be order 3. If the angle is 45 degrees, then the composition is going to be a rotation through 90 degrees, so it's going to be order 4, etc. Yeah? So these orders I can work out very easily, and I get a description of my group. Okay. So also, I said here, so there's this book, so the Zergel Bimodules book, which I meant to bring and forgot. So it's called Introduction to Zergel Bimodules. And there's chapter 2 written by me, which explains how to prove this theorem. Okay. And it's not difficult. It's like 2 pages or something. Yeah. It's just amazing, like how much incredibly detailed information you get out of these simple assumptions. Okay. So let's just see this theorem in action. So in this first example, so we're looking for, we're looking at affine reflections in these, in our integer points inside R. So our set of reflecting hyperplanes is the set of integers. And now we make this arbitrary choice of delta, which I've made in blue. Now, let's think about, so if we look at the composition of S1 and S0, so S1, S0 followed by S1. So what does this do, for example? So I'm looking at this now. So let's look at what this does to 1. So it sends 1 to 0. Sorry. So we reflect through 0 first. So it sends 1 to -1, and then -1 to 3. So it sends 1 to 3. This composition sends 1 to 3. 0, it sends 0 to 0, and then 0 to 2. And so we know that on this, it sends 0 to 2 and 1 to 3, and that's enough to pin down an affine isometry of the real line. So what this is it's a translation by 2. And so we can see that this is a fundamental domain. Yeah. So we can get everything with translations back to here, and then with our reflection we can get it back to here. So this is indeed a fundamental domain. Our theorem is not false on the first example, which is a good sign. We fix this choice. We look at, so now we claim that this group is generated by this reflection and this reflection, subject to the relation. So we've seen that S1 followed by S0 is a translation. Okay, so it's infinite order. And when something's infinite order, we apply the convention that this relation disappears. Yep, our relation is ST to the infinity equals 0. So that's kind of meaningless relation. Yeah? So our theorem still holds up with an important convention. What does it say in this example? So here's our symmetries of the triangular, this triangular lattice. So I've made this fixed arbitrary choice of fundamental alcove here. So this apparently enormous group is generated by these 3 reflections, which you can convince yourself of. It's a nice thought exercise. And we get the following presentation of our group. Okay. Because each of these, so if I look at the composition of this one and this one, sorry, this reflection and this reflection, so their composition will be a rotation through 120 degrees. So it's order 3. And so we get, you know, and that same argument applies to this one and this one. So we get these 3 relations. And we've just completely nailed down our group. It's kind of amazing. Okay. So, just have a few more notes to say about this, and then in the exercises, I'll show you the exercise, it's really fun exercise. Whoops. Okay, here's an infinite beehive. What's its symmetry group? No? Seems kind of complicated, but you can just use this and write it down in a couple of lines. Okay, so let me just say a few things briefly. So maybe I'll come back to this slide in a second. There's one thing that it'll come up time and time again, which is we have this left action. So, you know, W was defined to be a group of affine isometries of V. And so the way that our group is given to us naturally is we have this continuous left action on this space. So we have in this example, we have a vector space, we have all this nice decomposition and stuff, and W acts on the left as symmetries of this whole situation. Yeah. But we've also said, so one thing that I didn't emphasize, this is probably important. So in this example, I didn't emphasize this particular point, which is kind of amazing. So we've got these alcoves, yeah, so all these triangles, for example, or each of these intervals. And this is a picture of our group. So it's totally amazing. I think like if you say to me, consider affine reflections in integer points and consider the group generated by this, my first reaction is this is some crazy big group. But now I'm saying like every single, that this has, the elements are exactly parameterized by these pieces. Okay, so you can just see your group. And this is what happens in geometric group theory. So geometric group theory is the kind of study of geometry underlying groups. And often a geometric group theorist will be able to answer some crazy question about a really big infinite group because they can immediately see the group geometrically. Okay? So here's an example. So each one of these triangles corresponds to a unique element of our group. So we can just see all of our group elements laid out there. Okay. Yeah, so we have all our elements laid out before our eyes. And the question is, how do we transport the right action? So W acts on the left, and that's kind of obvious in this picture. How do we transport the right action? And that's important. So if W corresponds to W times, this is my fundamental alcove. Oops. Good old iPad static. Fundamental alcove. So the question is, what does WS look like under this bijection? So WS goes to WS of the fundamental alcove, which I can rewrite in a trivial way as W times S delta. Okay. So the upshot of this is that we have our fundamental alcove somewhere, and then one of these walls will be colored by S. So this is kind of S colored. Okay, so this is the wall that you go through in order to get to S. And what this is saying is that I can transport this color. So this is a fundamental domain. And so now I have this blue colored wall, and I can transport this right across my whole Coxeter complex. And this tells me how S acts on the right. Okay, it's important. And if I sound like a crazy person and this is not very useful, then that's fine. Like, it'll become more clear with time. Yeah. So the point is that the W action on the left on this picture is it's continuous, and it's automorphisms of the whole system. But what's really useful is the kind of right action of W on itself, because even though it's not a continuous, it's local. So if I'm here and I want to multiply by red, I just cross this red wall. Okay. So it's really very important to start thinking about. So you have this algebraic understanding of symmetric group or a Coxeter group or affine reflection group, and you have this geometry underlying it. And so how do you think about algebraic things in terms of geometry? How do you think about geometry things in terms of algebra? Okay, very important to start getting this bridge. So let me go through a few of these. So what's the length of an element? So if I have an element X here, it's really beautiful. The length is the number of reflecting hyperplanes that separate X from the identity. Okay. So it's very beautiful and very visual. Yeah. So that's the length. An expression is a stroll starting at the fundamental alcove. And so, like, here's a picture of an expression. Yep, so I go for a walk through this complex. And it's reduced if it crosses no wall twice. Is this reduced? No. So I saw about 7 shaking heads who would like, and also 1 nodding head, Who would like to tell me why it's not reduced? Perfect. Yep. So here's a wall that it crosses and then crosses back on. There's also another one that it crosses and comes back on. Yeah. So that's not reduced. Sub-expressions, very beautiful. So what you can imagine is I take this and I cut out a little piece of paper. Yep. So I cut, and then I just fold my little piece of paper. Yeah. That's what a sub-expression is. And Brouillard order is still tricky, but maybe we'll have an exercise on Leaviz where you can play with Brouillard order a little bit. Okay, so thank you and see you tomorrow. Do people normally ask questions or?
Yeah, there's opportunity for questions. There's
Chris?
So is it clear that it's the reduced expression that doesn't cross a wall? That obvious geometry. Is the question?
Chris is asking, is it obvious if an expression is that an expression is reduced if and only if it does not cross a wall twice? And I claim that if you've been thinking about this for a number of years, it is obvious.
a general rule that if it's not obvious to you, you should prove it. So it's an exercise.
Are there any questions from Hawaii?
I have a question. Do you hear that?
To some extent. It's
yeah. It's coming. Yes, so I have a question. So at the slide, there's an expression for, I mean, you were explaining expression like something 1 1 1 1 1 1 1 0 1 1 1 something like that. Yes, can you explain the diagram again? I don't understand this part.
so you're asking about what this diagram here means?
Yes.
Okay, so what I'm doing here is I'm looking at, so here we have 1 1 1 1 1 1 1, and so I'm looking at this Brouillard stroll, and so it looks like identity, whoops, identity, S, ST, STS, because my expression is, my sub-expression is 1 1 1 1 1 1 1. In every case here, I'm just taking the simple reflection. So this is ST, 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 STS, ST, ST, ST. Okay, so this is my stroll. Identity S, ST, STS, ST, ST, and you can work out that this is the same thing as TS, and this is the same thing as T, and this is the same thing as the identity. And so now my path is going duck, 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 duck. Does that make sense?
Yes. Yes. Yes.
Thank you.
Yes. So can you say again the following the lower diagram 1 1 0 1 1 1?
So if you're asking me about that, it probably means that I made a mistake. We will see. So this is identity S, ST, and now I don't take STS. So my next one is ST, and now I take STT, STTS, STTS. Okay, so this is, sorry, I think I'm messing this up. Hang on. So this would be STS0, STS0T1, STS.
The first one was correct, I think. Oh, but now it's still correct.
Okay, great. I'll slowly go crazy drawing S's and T's. But the point is that this is ST, and this is ST. This is now S. This is now identity, etc. Okay, so I'm imagining this walk as being ST, and then I kind of look longingly in this direction. This is where, you know, I should go if my walk had direction in life, but I say no, I'm not going there, so I come back. So that's what this little loop here means. So I go duck, 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 duck. Okay.
Okay, thank you.
Okay, so remind everyone that there will be opportunity to ask Geordie also questions during office hours at noon Brisbane time on Sokoko. And just a couple of comments that related to Geordie's comment about computer and maths. So his public lecture Thursday evening is about intuition coming from computer into mathematics and vice versa. So I encourage all of you, of course, to go there. And I also put a link from just a recent article I read in the bulletin about the philosophy of mathematics kind of, and discusses 4 color theorems, sphere packing, and related to what Geordie was talking about whether these are humane proofs or not. And there was also another link I put in there about another comment that Geordie made about how going to the affine version gives you extra intuition. And in fact, this was one of the first, or maybe the first application of affine Weil group, which was to classify torsion automorphisms of simple algebraic groups. And that was by Cartan. So I put a link to that as well, so you can read more about it. Otherwise, let's thank Geordie again.